We have a long-held understanding of how the universe's largest stars die. They run out of fuel, their cores collapse, and they detonate in an explosion bright enough to be seen across galaxies. But for years, astronomers have observed a significant accounting problem. We can calculate the number of massive stars currently running out of fuel, but the number of supernovas we actually see does not match that total. This chart compares the expected count of dying massive stars with the supernovas we have actually recorded. Somewhere between 10 and 30% of the universe's most massive stars are missing from the ledger. This discrepancy suggests that our mathematical models for stellar physics are incomplete, or that the universe is concealing the deaths of its largest suns. To find the missing deaths, astronomers focused on NGC 6946, a spiral galaxy 22 million light-years away. It is nicknamed the Fireworks Galaxy because it produces a remarkable number of supernovas, making it a primary location to catch a star in its final moments. In March 2009, a red supergiant about 25 times the mass of our Sun brightened into a faint outburst. For a few months, it burned with the light of more than 1 million suns, but it never exploded. This light curve tracks the star's brightness over 6 years. Following the initial peak in 2009, the line trends steadily downward. By 2015, the star had vanished from the optical spectrum entirely. There was no final blaze and no expanding shell of debris. This event provided the first physical proof of a failed supernova, the realization that a massive star can die with a whimper instead of a bang. For millions of years, the inward crushing force of gravity in a massive star is perfectly offset by the outward push of nuclear fusion. When the star runs out of fuel, fusion stops. Gravity takes over, and the outer layers rush inward. In a standard supernova, the core collapse releases a massive burst of neutrinos that create a shockwave, blasting the falling matter into space. But in a failed supernova, those neutrinos slip through. The shockwave stalls. Instead of being thrown across the galaxy, the outer layers continue to fall. The core swallows its own atmosphere, growing heavier and denser until a black hole forms and even light cannot leave the surface. Rather than the energy breaching the surface to light up the sky, the star feeds its own collapse. It builds a black hole from the inside out. Even when the core becomes a black hole and visible light vanishes, a physical signature remains. During its final moments, the star sheds its outermost atmosphere. This ejected material forms a shroud of cooling dust that emits a faint, persistent heat signature. While it is invisible to telescopes that see visible light, it remains detectable to instruments that see infrared. Optical telescopes see an empty patch of space where a star once lived, but infrared sensors can spot this glowing dust veil, the silent footprint of a failed supernova. Proving a broader pattern required a second observation. In 2026, astronomers found M31 2014 DS1, located right next door in the Andromeda galaxy. Researchers identified this star by searching through archival data from the NEOWISE mission. They looked specifically for the signature infrared flare followed by a total fade in visible light, finding a star that dimmed 10,000-fold by 2023. This is the interior of the Super Kamiokande detector in Japan. It contains 50,000 tons of ultra-pure water and thousands of sensors designed to catch the faint signals from passing neutrinos. Scientists checked the historical records of this facility to see if it captured a neutrino burst from Andromeda in 2014. The detector recorded nothing significant. This non-detection provides crucial evidence. The silence in the particle data proves that the star's collapse into a black hole was exceptionally gentle, lacking the energetic burst associated with an explosion. These silent deaths explain an inconsistency in data from gravitational wave observatories like LIGO. When these detectors capture the ripples of black holes colliding, the objects they record often appear heavier than what a standard supernova should leave behind. A supernova explosion blasts away a large portion of a star's mass before a black hole can form. A failed supernova does not. It keeps almost everything, providing a path to building exceptionally heavy stellar mass black holes. The night sky has likely always been doing this. Right now, a star is sliding out of the visible band, its layers falling inward as a new black hole is born without announcement. The universe does not always require dramatic violence to build its most extreme objects. Sometimes a sun weighing 25 times our own simply runs out of fuel, looks inward, and quietly falls into the dark.